Hello, good afternoon, everyone, and welcome to our second industry presentation. We are the Sterling Engine Capstone Group, and today we would like to share what we have achieved for our project with you. I'm Mihin Virkon, and my team members are Cameron Karg and Akash Karatmu. The goal of our capstone was to create an automated sorting system that can package 11 different parts used in a Sterling engine assembly that you can see on the right of this slide. This is currently done by hand by our client, Mr. Aman, before giving them to students who will assemble their engine in their lab classes along with a set of other hardware. Next slide, please. Today, we will go through our problem statement, our final designs, which are broken down into a feeder, hopper, ball bearing, and counting and bagging mechanisms, as well as our costs associated with this project, and finally, our conclusion and recommendation. There will also be a question and answer slide at the end, where we would love to answer any questions you have about the project. First up, our problem statement can be broken down into 5 sections. It should handle and pack the 11 different types of parts we are given. It should count the correct number of them before placing them into the bags. The bags itself must be resealable, and we will be doing this at a rate of about 1 bag per 2 minutes. This is all done to reduce the setup time for our client when packaging bags prior to giving them to students. You can see the different types of parts we'll be working with on the right here. We have multiple types of screws, washers, spacers, and bearing bags. Next slide. We have 4 main methods used to achieve the main goals of this project. We have a hopper that the bulk parts will go into, which is made as a part that can attach onto the main system if a larger quantity of parts are to be used. A feeder, which is the most important one, which will sort them and count and package, which will sort the parts. And then finally, we have counting and packaging mechanism. Now we have 3 initial concepts we created for a feeder mechanism. The first image is of a disc feeder. The second is a bowl feeder that we made, and the last is a drum feeder. We used a weighted objectives tree to cross-check our designs to make sure it fits the criteria, such as can it hold the right amount of parts, or does it get clogged when more parts are added? Next slide, please. Using our concepts and our weighted objectives, we decided that the disc feeder concept was the best, as the parts moved without getting stuck most of the time. We then further improved upon the design to create the designs you see on the screen. The first iteration uses a rotating plane and a thin ball that goes around it to orient and move parts. This sometimes got some parts stuck in the rails, so it is not perfect. We then made the design 2, which you can see on the second image, which is an added base plate for supports as well as a rotating plate that is designed to test many kinds of parts using different slot cutouts. This was done so we can test more than one kind of part at once and save time mainly on 3D printing. Both these designs we found out needed to be mounted at an angle to work effectively. So we created the stand. This is the stand that you see on the third image. Through testing, we found that the motor needed a dedicated mount for stability instead of only slotting right onto the base of the rotating plate. So we made our next stand design, which was more stable and had a motor mount. The half plate increased the stability, but it had times where it had the tendency to fall off the assembly if even a slight external force is applied accidentally. We then made our final design, using the knowledge gained from our previous test to create what you see in the final 2 images. This is an angled mount which clips onto a supporting plate like Lego. The walls and the rotating plate with cutouts mounts on top of it. The main benefit of this design is that we only need to change the inner rotating plate to sort multiple types of parts.
Disc feeder. So on the left, you can see the assembly of the disc feeder. And as this whole thing was to be 3D printed, we break down into many components that you can see on the right. So it has the main support, the motor mount, rotating plate, plate support, and the walls. The working principle is simple. All the parts are dumped onto the rotating plate, and as the plate rotates, the part gets stuck into the slot and are carried along with it to the top, where it leaves the feeder through an exit. Since it was supposed to be at an angle, the main support provides the required angles. It also has cutouts for motor mounts and wall mounts, and the mounting rails on the front helps to keep the plate at a proper angle. The motor mount is just a stand on which the motor slides from the top, and this can be directly mounted onto the main support. Here you can see the plate support, which has cutouts for the wall to be stuck in and an exit at the top for the parts to fall through. The walls are designed so that the cutout at the top can only allow a single part to pass through, and there are extrude at the bottom which acts as a support. Here you can see the drawings of the plate and the wall support, which shows the tolerances used to achieve a transition fit between those components. This image here shows the importance of the wall and the wall support. As you can see here, the wall support extends from the plate support and into the main support so that the whole system is a bit sturdier. Also, the inner groove makes sure that the rotating plate is aligned and the part falls properly into the slots. Rotating plates. The best part about the rotating plate is that they can be used for all the components by just changing the size and the dimensions of the part slots. Like the circular plate here can be used for the bushings and washers, whereas the figure in the middle shows the plate that has cutouts for the screws. The one on the right shows the cutouts for the spacers. Um, the figure at the bottom shows the sectional view. The figure at the bottom shows the sectional view of the plate, which has the motor mount for the motor to be attached to. The thickness is decided so that when the part is in the slot, it doesn't roll when the plate is rotating. Here you can see an exploded view of the installation of the disc feeder, about how all the parts stuck in together. And here's a working view of the disc feeder.
So now you see the three initial concepts we did for our hopper designs. The first is a disc hopper, the second one uses a rotating spiral, and finally we have a simple conveyor to move the parts from a parts bin to a sorter. Next slide. Out of these three, we decided that the disc hopper looked the most promising, as the parts consistently moved without clogging, and we used it as a basis when designing our final mechanism. This part was designed as an add-on item, which will integrate seamlessly with the sorter if a higher volume of parts are needed to be sorted at one run. This is what we came up with. It is quite similar to how our final sorter works, except we now use a modified ball with an exit channel and a flat plate with no slots. It is designed to be mounted horizontally onto the main support, which has a built-in motor mount for ease of use. Next slide, please. This is a section view of the wall we used. It is thick and durable, and it mounts onto a plate support, which will there itself mount onto a main support. The exit channel is where the parts will push into by the rotating plate and then go into a sorter. The wall can be easily made higher to support more parts if needed, as this supports it fits onto are very stable. Now you see a section view of the rotating plate that goes onto the middle of the hopper. It's a very simple design where the motor will fit onto the base and spins the plate, thereby moving the plates into a sorter, parts into a sorter. Next slide, please. This is a short video on how a hopper is assembled.
Hello. Now when it comes to bearings, bearings is one of the parts we didn't really get to. It's a singular part that comes like seen in the picture in the center. This then, as a bulk parts come in like a Ziploc bag with lots of parts. So our first design on how we would sort them were on a conveyor where all the parts would be placed down, and then as it was moving, there would be bumpers that would bump it to the center, where it could then be counted. Next would be a magnetic counter. This would be the bearings would come down on the slider, where the wheel would then rotate with embedded magnets that would pick a bearing up at a time so it could be counted. Another idea was to use a vacuum or some type of gripper that would grab a bearings from a pile. Next is counting. So first, after they come out of the feeders, they must now be counted. So we had three main designs. First was mechanical, and then photoelectric sensors and magazine counters. We ended up going with the photoelectric sensors as they were the least amount of maintenance and easy to implement. So once we had the counting mechanism we wanted to use, we then just had to make a simple model that could be connected to the feeders. So the model just has a little hole in it that is specific for the different parts. So this can be slightly changed or modified to the different parts by just changing the diameters. You can see it printed on the far right picture there. And then next up, we have bagging. Bagging is another thing we didn't get fully implemented. Our main ideas were using cups that would move across a conveyor, or Ziplocs that would move across a conveyor, or they could either of them could also be used with a robot. And then they both need to be shut and then put into storage. Next is cost. With cost, we broke it down into three main groups. We have parts, tooling, and labor. So on parts, the main ones are the motors and sensors that have to be used for each of the orders. And then for tooling, we mainly did 3D printing. So of course you need a 3D printer to do that. And then labor, we have most of this time was spent on developing our skills and working on the design, getting it to the full standard. to work with the parts. So in conclusion, we went through our problem statement, our final designs, including our feeder, hopper, ball bearings, part counters, bagging, and also our cost. For recommendations, we recommend taking what we have here of our 3 different designs that work for all the types of parts, excluding the bearings, and scaling it up to work to package all of the different parts. So as you can see, we have a sorter that works for the cylindrical parts, the washers, and also the screws. On the next slide, you can see that we have them counting as well. So yes, we'd like to thank you for listening, and we can now take any questions.
Hey Cam, it's Chris. Apart from the bearing, which part was most challenging for you and why?
The bearing was challenging as it was a part that it wasn't sturdy, right? So with the package itself, it was in a bag. So when it
sorry, apart from the bearing.
Oh, sorry. What was that?
Apart from the bearing, the next most challenging one.
I would say there's a little hex nut that's really it's a very thin part. So it's very thin and small. I think it's maybe a couple millimeters in diameter by a millimeter or so in depth. I don't know the exact measurements. That one was very hard for even getting a 3D print that would sort it, as it would, because even the 3D print then has to be super thin. So it has to be pretty accurate for printing. So I found that one was definitely difficult to get a good plate that would work for it. Yeah.
And it was successful?
Yes, we did get one that was working pretty well. Sometimes it wouldn't. We had a couple variations, but eventually we were able to get the ones that the washer parts to fall in and get counted.
Excellent, because I was thinking that was going to be a difficult part. Excellent, well done.
Yes, it was. Any other questions? All right, I'd like to thank you guys all for coming and listening to a presentation.
Thank you very much, team.